Hello class, welcome back. We're in chapter 4 here of statics class, and we've been talking about the reduction of force and couple moment systems, basically reducing a problem where you have many forces and possibly a combination of forces and moments or many couple moments acting, and we reduced it to a single force, single moment, whether it was about a point or about an axis. And 4.8 is just a short section that adds on to that to further reduce that. We want to go from a single force and a single moment, possibly just to a single force acting at some distance from that original point that gives us the same effect as those forces in that moment resulted. So we're going to walk through that. Just a quick example here in 2D. 2D, what we're looking to do is if we have, force 1, force 2, force 3 acting on this beam or this structure out here, and let's say we want to reduce that to a single force. Okay, reduce that to a single force and resultant moment. Now that force doesn't necessarily have to be where I've drawn it. I just want to show that we're taking those forces into a resultant force, and because those forces acting at these distances, we can put that into a resultant moment. So that's force times distance. This is going to be adding up all the forces. So that was really section 4.7. 4.8, we want to take it even further and say, hey, can we adjust where that force resultant is, and can we move it out to a new spot that would actually give us not only that resultant force, equivalent force, but also account for this moment set up by those forces about this point here. Could we reduce that out and just have that everything be in sort of one resultant force? And that's sort of the further reduction. If we're in 3D real quickly, and you'll see this when we get to problems, I just want to walk through some just sort of generic. If we're looking at, we have this here in 3D, let's say we go through the solution and we're finding everything about point O. We find out that there's a force here, our resultant force, which is adding up all the forces. And let's say about this negative x-axis, we have a resultant moment, and that was counterclockwise, so that's in the negative x direction. If there's the x, there's the y and the z. We have a special case where they are perpendicular. We could move that force out here, move that force back here a distance d, and have that resultant force act there, and at that distance it would create or be the equivalent resultant moment of that. So the force gives us the force result, and that covers that. This force moving that distance is going to equal that force resultant times the distance. So we're looking at how we can further simplify this, because again, our whole plan is to get this problem or these results or now our analysis off the strength material folks or whoever's coming next, and to be able to reduce it as much as possible so they don't have to go through finding moments more. We can just give them a simplified version as possible. Okay? So further reduction, 4.8, talking about that. And the way we want to go about that, again, is our resultant force is going to be adding up all the forces, whether that's in 2D or 3D, and then we're going to find the resultant moment, and that's going to be summing up all the moments, and we'll set that equal to that resultant force acting at some distance, and that force acting at distance will give us the same effect, so we can reduce it to a single resultant force. Okay? Now, within this, there's also a term that comes up called wrench. And a wrench is a very special case when we reduce it to a single force and a moment, and they're not perpendicular, it's in the case where we'll end up having a resultant force, and we also find the resultant moment happens to be about that same axis. And that's the idea of a wrench. It's more of a, wrench I think of with a bolt. I think of this more as almost a screwdriver, but I didn't write the book, so I can't call it what I think it should be called. But the idea is sort of we're applying this way, sort of screwing it this way, or if it was the other way, we'd be screwing it down or loosening it, things like that. Okay? And we can come up with this idea of a wrench, and it's drawn that way. Sometimes they put a double arrow in there, one to show the moment, and the other one up here to show the resultant force. Okay? So just real quick over, we're just trying to further reduce this. I want to go through and do a couple of 2D problems and a little bit of 3D problems, just so you can see what's going on. This should sort of tie up and further confirm what we did in 4.7. And what I'm going to do is put up an image here and pause recording so I can clean off the board, and we will go from there. So let's see if that works. Okay, we're back. It took a lot longer than what you saw there on the computer, but we're back and it's good to go. All right, so let's do a 2D problem here. We're going to be given this drawing here. We'll have a simply supported beam. We talk about that in a later chapter. Simply supported means it's really just connected on one end. So it's fixed there at point O. We're going to have a force here of 30 up. We'll also have one here that's sort of a 20I plus 20J. That will be completely J. And we're going to have a couple moment here that's 210 Newton meters counterclockwise at the end. Give it some dimensions here. Let's see, 3 to here, another 2 to that one. Okay. Not really concerned about the additional length here because I don't know how many forces acting. That's a couple moments. Again, couple moments are free vectors. We can slide those anywhere we want. So we're not concerned about them as far as needing a distance there. All right, so we're asked to find the single resultant force and moment acting at O. And O again being the origin. This is 4.7, so we're just going to do what we've done before. Always, to get the resultant force in any problem, we sum forces. Okay, shouldn't be anything earth-shattering right there. If we go through and add that, I'm going to do this on the fly, and I'll do it. We're going to stay in 2 dimensions there. We add the i's together, so we're going to get a 20I. We add the j's together, we get a 50J, and that will be all newtons. Okay? All newtons. Now, I could find the resultant magnitude, square root of the squares. I can find the angle, the inverse tangent, but let's just leave it as it is there. It's fine as it is. All right, what about the resultant moment? Well, the resultant moment is going to be a O. We're going to call positive counterclockwise. Is what we traditionally do. That means we're going to sum up all the moments acting about O, which means we're going to sum up all the force times distance acting there. Okay? Keeping in mind about the signs. So if I just work from left to right there, I'm going to have the 30 up. That's acting at 3 meters. That's this way, so it's positive. I'm going to have the 20. That's the J component, acting at a distance of 5 meters. That's also counterclockwise, so that is also positive. Now, what about the 20 in the I direction? Well, 20 in the I direction is this way. It pulls directly through point O, so I could add it in here, right? I could put the 20I, but that distance is 0 meters, so that goes to 0. This component of 20 here in the I direction or X direction does not contribute to creating a moment about O. And then we can't forget about the 210 over here. That's in the same direction. That's 210 Newton meters also that way. Positive. And if we go through all that mess, what we're going to come up with should be 400 Newton meters. And since we picked positive that way, I don't have to include the arrow, but I will just to remind myself that it's counterclockwise. So reduce this up here, two forces in a couple moment to a single force and a single couple moment acting at point O. Okay? Acting at point O. Now, what we'd like to do, or what we could do, is we could redraw this. And there's point O. I'd put that there. I'd make the moment of 400 Newton meters. And I could also put it in that force that's acting there. It's going to be more vertical than horizontal. And that becomes a 20 and 50 if I put it in that notation of I and J. So that tends to be an equivalent system right there at point O. And I could pick any other point. The 400 is slidable. It's a free vector. So we have that. But what we want to do here in 4.8 is do that further. Reduction. And the further reduction means I'm going to look at, can I slide this force to a new location so that it also, along with it being the force, it gives me the same net effect as that couple moment. Okay? Now, again, the I component doesn't do anything contributing to that moment. It's only in the Y direction. So I'm really looking at this one here. So what I need to do is I'm going to say the resultant moment at O, resultant moment at O, has to equal that resultant force acting at some distance from O. Meaning I'm going to slide this force to a certain distance. What do I have to have it equal to? 400. What is that resultant force? Well, again, the Y component's the only part of that force, that two-dimensional force that's creating rotation, so that'll be 50, right? That's in the J direction. Times D, I go through and solve that, I get D equals 8 meters. Okay? Now, what does that mean? That means I can now redraw this and simplify it even more. If I slide that force out to a distance of 8 meters, wherever that is, again, we kept it here at 5 and then undisclosed amount here. We're going to assume it's long enough that we can make it to 8 meters. I have that force of 20 I 50J newtons, that's my resultant force, acting at 8 meters. What it does, it gives me the resultant force, 2050. It also gives me 50 at 8, which gives me a couple moment of 400, which also gives me this value. So what I've done is taken these two forces in couple moment, reduced them to a single force and moment, and now reduce them further to a single force acting at a new point. Good problem there in 2 dimensions, just sort of to get you started on that. I'm going to pause the video again, and we'll come back and do another problem or two just before we finish up this lecture on 4.8. So I will be back. Okay, we're back. We're going to do another 2-dimensional problem here. One out of an old textbook. Let's see if I can bring this up. And actually, I think we're going to do that problem. Hopefully you can see that. I'll try to make it a little bit bigger. There we go. Okay, we have a truss here. We'll learn about trusses in a later chapter. It's basically multiple members to give us some structural rigidity. They're meant to support vertical loads. So we're asking this problem. The system of parallel forces acts on the top of the Warren truss. Determine the equivalent resultant force of the system and specifies location measured from point A. So again, we are looking to find the single resultant force at some point, and I think they're calling it, or from point A. So at some distance, D, we could use X. They just tend to use D because we're sliding it, not, a certain amount along the X direction, although it is, but we call it D because it's a unique distance we're going to have there. All right, it's not saying anything about the equivalent resultant moment, but that's going to be an intermediate step we have to go through. Okay? So how do we do this? Well, we already know how to do two things here. We sum forces and sum moments. Now, since all the forces happen to be down in this problem, I have to be careful. I wrote all that up there, and you can't see what I wrote. Let's try this. Maybe that's better. All right, single resultant force at point D from point A. We have to sum the forces. Since all the forces are down, I'm just going to pick positive down. Because if I pick positive up, I have to rate them all as negative. There's really no reason to do that. So we're going to sum all the forces, and we have what, 500. We have 1 kilonewton, so 1,000. We have another 500. We have a 2,000 there, and on the end we have another 500. 1, 2, 3, 4. If I go through that, 4,500 newtons. Now, if we were given everything in kilonewtons, so that's 0.51, 0.52, 0.5, I'd put my answer as 4.5 kilonewtons. I'm just going to stick with newtons. So there's our resultant force. Okay? There's our resultant force. Now, to get the moment and then get into the distance, our resultant moment has to be that 4,500 times a certain distance. Okay? But let's find the resultant moment. Instead of trying to do one step, which the book sometimes does, all in one step, let's do it in 2 steps. Let's find the resultant moment about a point. And since we're measuring everything from A, I'm going to find the resultant moment about point A due to all those forces. It's an intermediary step compared to what the book does. I think it just makes more sense if we do that. So we'll have the 500 acting at 0. That does nothing for us. And, we usually have the moment this way. Let's do the moment this way because we're about point A. Everything is pushing down. It'll just keep us all the positive signs. We can do that. It's all good. All right, so we have that. We have the 1,000 acting at a distance of, 1 meter up there. We have another 500 acting at 2 meters from A. We have a 2,000 acting at 1, 2, 3. And then the last 500 is acting at 4. And what's that? It goes to 0. So there's 1,000, 2,000, plus 6, 8,000, 10,000. 10,000 Newton meters. Okay, 10,000 Newton meters. So this would be a 4.7 solution where we go to a single resultant force, single resultant moment, done. Again, this is a free vector, so I say it's about A, because that's where I got all the generation of those distances, but it's a free vector, so we could slide it. Now, to get that distance, we want to take that resultant about A equal to the resultant force that we found in that first step times that distance measured from A. So that's going to be 10,000. That's 4,500 times dA, distance from A. And if I go through that, that's twice. I think it comes out to 2.2 if I did that solution correctly. So if I redrew that, you can't see it because it's my hand. If I can get above it, no, I can't get above it there. It would be somewhere right around that 4,500 would be somewhere acting right about here. So a little off center. Now, does that make sense? I'll just sort of put it right there, right? Does that make sense for that distance? Well, if we look at that structure right down the center here, we have 500, 1,000, 500 in the middle. Here we have 500, 2,500. So we actually have more force acting on that right side. So it does make sense that it's skewed that way towards the greater force. So I'm okay with that. I feel good about that solution right there. All right, we're going to come back and do one in 3 dimensions and finish up this lecture. So let's go to that standby mode. Okay, welcome back. We're going to finish up this lecture session here with a 3-dimensional problem I have up in the corner of the board there. And it's a little hard to see, but I've rewritten what the force vector is and also what the moment vector is. And we're asked to find the equivalent resultant force and couple moment acting at Q. Okay, acting at Q. All right, so let's go ahead and do this problem. Again, we have to find the single resultant force and then find the resultant moment and then apply them to point Q if we have to adjust them. So first step, find that resultant force. Again, it's a vector. That means we add up all the forces acting in the problem. Okay, this one's going to be tough. You ready for this? How many forces are acting in the problem? So when I sum all the forces, what am I going to get? That one force. I get the 8, 6, 8 newtons done and done. That's my answer. That is literally my answer. If there was another force acting up there off at some other point, I would just have to include that and add that with that answer. That's it. Okay? What about the resultant moment? Now we're told to find the resultant moment about Q. So I'm going to add up all the moments about Q. And because of our situation, the first moment is going to be the R cross F. And that R is going to go from point Q to the force. And that force is acting at, well, I don't have a point up there. We can call that, I don't know. Well, we can't use P because that's already in there. They already have O. Well, we'll just call it A. Doesn't matter. All right. So that's going to go from Q to point A because it has to go to a point on the force. I'm not going to try to pick a different point on the force. That's a given one, even though it's not labeled. And we'll go through there. So that's going to be the moment due to that, plus the moment that is given to us. I'll just write that as given. And those are the only 2 characters in this play. Right now we have a force that causes a moment about Q, and we have this free vector moment right there. Again, it's a sliding vector. We can put it anywhere. Even though it's acting at a point, it is a general couple moment on that entire system. We're just seeing the axes here. We're not seeing the actual problem, but that's a sliding vector, so that's the 2 we have to be aware of there, include. So if I build this 3 by 3, again, we have the I, J, and K. Position vector has to take us from Q to point A. Point A is the application of the force. So in the X direction, I have to go 0, right? Because Q is lined up at the same distance behind the origin. In the Y direction, it looks like I have to go over 5. And the K direction, I have to go up from the Q level to the A level, which is another 5. And again, I think it's really helpful just to walk that to make sure you didn't make any mistakes, because I was sort of doing that on the fly. So go from point Q to point A, I have to walk 0 in the X, plus 5 in the Y, and plus 5 in the K. And the image is obviously up there. I'm looking down here because I can see it on my monitor. So that's that. What do I cross that with? Well, I cross that with my given force, which is 868. And with that, I add to that, I add the result, or the moment there, the 20 minus 70, 20. And that takes care of the 2 I have in there. Okay? So the resultant force acting about Q, and then the given moment, which is a free vector, we add that in there. If there was a third force, we'd have R cross F here, or a second force, R cross F, the second force about Q, and then we'd add that moment. If there's more moments, we just add more moments. It just becomes an accounting problem at that point. So if I go through all that mess, I should come up with a final answer here of minus 10, minus 30, minus 20 Newton meters. So to answer my original question, the resultant force, this one right here, resultant couple moment, this one here due to the force acting at Q, and the given moment. Now, if I picked a different point, obviously this value would change because this value right here, this position vector changes for the R cross F. This doesn't change with the R cross F, which would change the answer. And that's just our 3D problem. Okay? Nothing new here. We sum forces, we know how to do that. We sum moments, we should know how to do that. Those are the 2 things for statics. So the foundation pillars we stand on, sum forces, sum moments. Up till now, we've set them equal to 0 to make sure we are in static equilibrium. Now we're finding what that result is, and then we'll use that result when we talk later about support reactions on the whole entire structure. Makes thing this, even once we know this result, we know that the structure will be held up by the supports, whether it's the ground or the walls or bridges or whatever it's held together. All right, so that's it. Any questions on this? As always, shoot me an email. Catch me before or after class if you're on campus. And otherwise, hang with the videos. I appreciate any kind of feedback you can provide. This is only like the second or third I've done with this new glass board. Still trying to figure things out. Still trying to get this color thing figured out so I can get different colors. And obviously getting the image in the correct spot so it is, so I'm not writing behind it and things like that. So, all right, that's 4.8. Hope you have a great day, and some forces, some moments, and we will talk to you soon.